In the previous video, we looked at a method for solving second-order linear non-homogeneous differential equations. This method is called the variation of parameters. In this example, we're going to apply this method for a non-homogeneous ODE, given by this equation over here. So recall that the general solution for a non-homogeneous ODE is equal to YH plus YP, where YH is the solution for the associated homogeneous ODE, which is called the complementary solution, and YP is equal to U1Y1 plus U2Y2, where U1 and Y2 are functions of x of the dependent variable, and Y1 and Y2 are the fundamental solutions obtained from the homogeneous ODE. So before we can tackle the non-homogeneous part, we need to look at our associated homogeneous ODE. So what we do is that we set the right-hand side to 0. This is a constant coefficient ODE, so we can look at the characteristic equation, which states that r squared plus 2r plus 1 is equal to 0. We want to solve for r because our solution will be of the form e to the rx. So solving this characteristic equation, we find that we have r plus 1 is equal to 0 if we factor this equation. Which leads us to the conclusion that r1 is equal to r2, and both are equal to -1. So we can say that this is equal to r. And we have seen in a previous video that when we have two equal roots, our fundamental solutions are y1 is equal to e to the rx, and y2 is equal to x e to the rx. Therefore, we have y1 is equal to e to the negative x, and y2 is equal to x e to the negative x. These are our two fundamental solutions, which allows us to say that the homogeneous solution, YH, which is the complementary solution, is equal to C1 e to the negative x plus C2 x e to the negative x. So we have solved the first part of the problem. Now we need to deal with the particular solution. So we need to evaluate the parameters u1 and u2. From the previous video, we have seen that u1 is equal to the negative of y2 r of x divided by y1 y2 prime minus y1 prime y2 dx, where the denominator is just the Wronskian of the functions y1 and y2. So let's go ahead and evaluate this. So we have the negative of y2, which is given by x e to the negative x. Then we multiply this by r of x. Now r of x from our ODE is given by e to the negative x ln of x. We then divide this by the Wronskian of the two functions y1, y2 prime. So this will involve a bit of calculus, but it's not too bad. So y1 is e to the negative x. Now y2 prime, so we need to take the first derivative of y2, which will involve the product rule. So this gives us e to the negative x minus x e to the negative x. Then we have minus the first derivative of y1, which will be equal to negative e to the negative x, multiplied by y2, which is x e to the negative x. Now this will involve a bit of algebra, a bit of grouping of terms to simplify. But what we find, after some simplification, is that this integral is of the form x ln of x dx. I invite you to pause the video and try to come to this same integral. Now this integral can be found in any standard integral table. And so here is the solution for u1. We're nearly there. Now we need to find a solution for u2. Now u2 is equal to the integral of y1 r of x, our non-homogeneous term, divided by the Wronskian of y1 and y2. And what we find is that this gives us the integral of ln of x dx. And again, I would encourage you to pause the video and try to come to the same form of an integral. Evaluating this integral, and again, you can use any integral table, you will find that it is equal to x ln of x minus x. And here is our solution for u2. Having found u1 and u2, we can find an expression for the particular solution yp, which is equal to u1 y1 plus u2 y2. We found u1 to be 1 over 4 x squared minus 1/2 x squared ln of x. We multiply this by y1, which is e to the negative x. Then we add u2 y2, so we have found that u2 is x ln of x minus x, and then we multiply it by y2, which is x e to the negative x. I would encourage you to try to evaluate this expression. After some simplification, you'll find that we can express it as x squared over 2 ln of x minus 3x squared over 4 divided by e to the negative x. So putting everything together, we have our general solution, y of x, that will be equal to c1y1 plus c2y2. That's the associated complementary solution. So c1 multiplied by y1, e to the negative x, plus c2 multiplied by y2, which is x e to the negative x, plus the particular solution, which we just found above here. That is x squared over 2 ln of x minus 3 x squared over 4 e to the negative x. So the process is a bit labor intensive, but in general, the integrations are fairly straightforward.